Hello, welcome everyone. So it's a pleasure to have Professor Soeren Schlichting with us. Soeren has been working on the very intricate stages of the initial stages of heavy ion collisions, both from lattice as well as from kinetic theory and perturbative theory approaches. So he will share his own thoughts about this initial stages. And sorry, here he will tell us more about jets, and which is also from the initial stages perspective mainly, but also in the thermal QCD. So I give it over to Soeren. Thanks.
Yeah, thank you very much. And I mean, of course, it's a great pleasure to be here. So as announced, what I will try to cover a little bit in this introductory lectures are the way that jets, and as I'll say quickly, I'll have a rather loose definition of what I actually mean with a jet, how they interact with the thermal medium that we create in heavy ion conditions up to the point, and I hope I get to where I covered this, where actually we can even, if we embed a jet in a medium and we wait long enough, we can actually thermalize the whole thing inside the medium, and that's of course physics connecting to what I'm primarily working on, is sort of, how can we understand non-equilibrium dynamics and thermalization of the Quark-Gluon plasma. So since this is somehow the first talk in this aiming in this direction, so let me just put this into a little bit of a frame, and sort of the majority of the lecture will actually be on the blackboard, but I wanted to just give this some context, right? So why are we doing this, and sort of what do jets or high energy particles sort of add to the picture? Okay. So when we study heavy ion collisions, somehow we produce this deconfined and chiral symmetry restored QGP, and really we're doing this with, in the intent to sort of understand and characterize the properties of this medium. And there, the story is that because we're doing this not in a lattice calculation, but in some kind of experiment, okay, that's dynamical, that provides us with different probes of the Quark-Gluon plasma. And sort of on the one hand, we have the typical degrees of freedom, which is the plasma that we have. So let's say they have typically energies maybe of a GeV or so, okay, so typically on the order of the temperature. So particles we measure at the end may have GeV energies. And there we see all the soft QCD physics, phenomena like elliptic flow, the QGP behaving as an almost ideal fluid. And if we understand sort of this dynamics well enough, right, then we can learn about near equilibrium or transport properties, equilibrium properties like the equation of state by studying the outcome of a heavy ion experiment, okay? But then there's the great thing, is because we're doing this in a collider experiment and not setting this up as sort of a black box, okay, we are also a static equilibrium system, okay, we are also provided with this exceptional hard probes, which can have energies that are much larger than the temperature, so we can have jets with hundreds of GeV energy realized, and that is very interesting from different viewpoints somehow, okay. So the first thing that, and then this was sort of, maybe more the traditional way of coming at it, that you can say is, okay, well, if I look at a 100 GeV particle or so, a 100 GeV jet, right, then that's really a hard QCD object, okay, so, and that immediately rings a bell, because you could think, okay, well, if this is a high energy probe, then this really seems like I can have perturbative control of this object, and I would hope that maybe this can act in some way as a calibrated probe of what I'm doing of my Quark-Gluon plasma. Well, for certain aspects, you can think about it like this, okay, but at the end of the day, it turns out that when you actually describe how such an object interacts with the plasma, also you're basically back down to doing a lot of soft physics, and there is a lot of theoretical uncertainty involved with that, okay, and I'll try to describe this also in this lecture. But that's not the only reason. I mean, the reason that I find these things actually particularly interesting or exciting is that this is really something, okay, that we cannot study in an equilibrium system, okay? If we put just a particle in our system which has an energy that is much higher than the typical energy of the thermal excitation, so this is really a non-equilibrium situation somehow, right? So this is really a non-equilibrium perturbation of our Quark-Gluon plasma, okay? And so this is actually very interesting to sort of study in its own right? So, how does that sort of part of the system evolve, right? And what are the features and the dynamics that one observes there. So this is really doing non-equilibrium QCD from that point of view, right? Then you can ask the question, okay, so I put this up sort of a little bit placative, right? You have sort of this very soft stuff and this very high energy stuff. So now where do you draw the boundary between these two things, okay? And I mean, actually drawing the boundary is somehow a dynamical question, right? I mean, at the end of the day, right, if you put something which is very high energy, right, and you know, that'll take a lot of time to sort of lose energy, thermalize, and so forth, right? But this sort of, so there's sort of a sliding scale on, you know, what you should consider as being highly energetic or being a jet, right? And what should be eventually maybe become part of your thermal system, okay? And so this is why sort of studying the physics of jets, I think also very much connects to other questions that we have in heavy ion physics, like how do we form an equilibrated Quark-Gluon plasma in the first place, okay? And what is the physics maybe at this intermediate scales, right? And this is an area that is maybe not so much explored yet, right? But I mean, if you were to study sort of really systematically sort of hard but not too hard excitations and really understand their features really well, I think this should tell you a whole lot about sort of how thermalization can happen in a Quark-Gluon plasma. Good. Okay. So this is sort of, you know, why I think this is very interesting. So let's at least have a little bit of a theoretical background here on what actually jets are, or what is the common framework that these things are described. Okay. And so if you first look at any hard probe, or you can actually take a jet if you want, so in a PP collision, okay, then the way that you theoretically describe this is actually very well controlled, okay, because you can exploit the separation of scales where sort of different things, of time scales where different things happen sequentially, okay, to factorize production cross-section for these things, okay. So I actually wanted to put down the cross-section formula for something like an inclusive hadron production or jet, but basically it takes the following structure, okay? So the picture that you have is that sort of when two protons collide, the first thing you need to pick out some hard partons from your colliding hadrons, okay? So let's say this can be highly energetic quarks or gluons. Then there is a scattering process with a large momentum transfer. So that's something that, again, can be calculated perturbatively, order in order by perturbation theory, okay? And then following this production, essentially, you have emission of radiation and eventually degrading the virtuality down to soft scales where things hadronize, okay? Again, in this question, there's non-perturbative physics involved. On the one hand, what is the partonic content of nuclei, okay? And on the other hand, how do partons form hadrons if you detect hadrons? But this is encoded in universal objects, okay? And so you can describe this, which you can determine, okay? Either, for instance, the parton distributions you could determine on the lattice, okay? Or in other experiments like fragmentation functions, you could measure in E plus E minus two hadrons, okay? And so this gives you a controlled way of computing things, okay? Now, particularly nice is then to look at what is actually a jet, okay? Because a jet is sort of trying to get you more to this parton level kinematics, okay? So if you actually study a jet, okay, then what you're doing is you're basically these are defined as infrared and collinear safe objects. What does it mean? So essentially, when you look at a parton, then the parton emits radiation. Okay, that radiation likes to be close to the original parton and carry small energy fractions. Okay, but that doesn't somehow change the energy flow very much. Okay, and so if you sort of cluster things inside some cone, okay, and you need some prescription to do that, that's called the jet algorithm, okay, then that really allows you to match essentially perturbative theoretical calculations to what you do in the experiment, okay, and that's a way of doing precision physics, okay, which is really what jets are being used for in, let's say, PP or, I mean, you can also do this in whatever, electron-ion collisions or so, and there are proposals to use this to really do precision determinations of alpha S and things like this. Okay, now what we're interested in is that is now what is happening in a heavy ion collision with this setup, okay? And so the initial stages of this, of course, don't change very much, right? So now if we do this in a heavy ion collisions, instead of having, the starting point is the same, right? So we start with somehow hard partons that we now pick out of our nuclei instead of out of a proton, okay? There's also a hard scattering that leads to the production of these highly energetic particles. But then, and that's because it's a hard scattering process, it's a very short time scale associated to this, okay? So these guys are sort of there from the very beginning, that the surrounding medium is present. But then life becomes a whole lot more complicated because everything what happens afterwards, okay, so emission of vacuum-like radiation, additional interactions with the medium, okay, and they affect, of course, radiation, hadronization, this now all happens inside the medium, okay? And so this is, of course, where the interesting but also complicated part takes place, okay? And so if you study this field, right, I mean, then there's a lot of different aspects that sort of can take place here. And so, for instance, you can look at things where still, you know, and so what you find out actually depends a lot also on what particular observable you look at, right? So, I mean, for instance, if you say, okay, I measure jets with 100 GeV, okay, the first requirement that you have is that 100 GeV jet actually makes it out of the medium, okay, and didn't lose a substantial amount of its energy somehow to the medium, okay? So, a lot of the times when you look at the observables, you actually have to very, very, very precisely understand sort of what is the thing you're actually looking at. And so you can sort of, different observables are similar to different things. So a lot of the observables we measure are actually still very much related or inspired from PP physics. So for instance, investigating sort of the detailed structures of the jet, and then you're mainly sensitive to sort of how the physics that otherwise, this physics of branching that you see in the vacuum, how this is modified by the presence of the medium. And there's a huge class of sort of substructure observables that actually go in there. Okay? The other thing you could ask, or structurally you could ask, is somehow how for instance, the jet can actually deposit some of its energy into the system. Okay, and this you see, for instance, in observables by measuring things like the jet RAA, or you could imagine doing recoil measurements where, I don't know, you look at photon jet or so, and you look at the jet spectrum on the recoiling side of the photon. So there's a huge phenomenology here, okay, that I'm not going to be able to cover about, okay. So, but I think you will hear more about this in the lectures next week by Peter Jacobs, okay. Because what aspect you're probing really depends very much on the concrete observable that you're looking. So for me, okay, so what I'll do in these lectures, okay, is I think what I want to do is I want to give you sort of a little bit of a flavor of what are the sort of the basic building blocks of when we start to now embed these hard probes inside the medium, okay? And so I will very much focus on the medium interaction of a hard parton of jets with the medium, okay? And I'll go through this in kind of this sequence. So, of course, what can happen? Well, what can happen is there can be exchange of color, okay? And there will be also exchange of momentum. This we call momentum broadening, okay? The other thing is that, of course, if you exchange momentum with the medium, then you have color-charged particles that are being accelerated, so there'll be additional radiation created inside the Quark-Gluon plasma. So I'll talk about this medium-induced radiation, okay? And then I very much hope to get towards the end to also then the ultimate question, if we, you know, what happens if we spin this sort of ultimately long, so we let the jet really pass for a long time to a Quark-Gluon plasma, what is the dynamics that eventually leads to the thing becoming part of the plasma, yeah? So what I mean is that basically you have, I mean, you only have the hard scattering, okay, and nothing else happening, right? And then, so I mean, so if you were to calculate this process at the tree level, you would have sort of a 2-to-2 cross section, right? But then, of course, you have to include all the radiative corrections, right? And it turns out you have to resum these radiative corrections, and this is how the I mean, there's a large phase space for emitting radiation, yeah, and so you need to resum this, and this is what leads to this development of this parton shower, yeah. Yeah, so a simple PP collision should be, yeah, it should be close to a vacuum shower. Yeah, yeah. I mean, that's what I mean. Yeah, yeah. Okay, and so one thing I should say that, okay, I mean, so I told you in principle, if you say a jet is a, you know, I'm talking about you're talking about the jet, then really what you strictly should have in mind with this is you have a jet algorithm defined with its parameters like the cone size. Okay. Now I'm a person who's actually most interested in what happens if the jet is lost. Okay, or so throughout my speech here, I will, and there are events like this, right? So you can look at sort of detected particles in heavy ion experiments where you see, you know, you have a huge jet peak. So these are energy towers on the one side, and there's basically nothing to balance this momentum. Okay, so I will always adapt. So whenever I say jet, I never mean like something which is reconstructed by a cone size, but I generically just mean something that is sort of very highly energetic inside the medium. Okay, good. So this is roughly the outline of what I want to cover. I think with this we can actually completely pull this up, and I will go to the blackboard. Okay, and so the first thing I want to cover today is the interaction of a high energetic particle. So high energy particle in UCD matter. Okay, I know my handwriting is not so great to read, okay, but I'm going to say everything, and if you cannot read something, just, you know, just interrupt me and ask what you want to ask. Okay, so what is the picture we have? Okay, or what is the problem we want to understand? Okay, so we have some kind of blob of, in our case, a Quark-Gluon plasma, but I should say that, so actually the basic way that sort of the theory works, okay, applies not only to physics of hot QCD, but in fact, if you're doing calculation of cold nuclear matter, so for instance, calculations of saturation physics or so, they are actually built up in a very similar way. Okay, so a lot of sort of the formalism that one uses can be also adapted to other problems in high energy scattering in general. So we have our sort of QCD medium, okay, and so if we think of this as having some kind of constituents, and the typical constituents have energies of the order of T, right? But then what we actually want to embed here is some hard parton, okay, with an energy that is much larger typically than the temperature of the medium, okay? And so in order to describe the propagation of such a hard parton in QCD matter, it is advantageous to adopt these so-called light cone coordinates. Okay. So what we're going to be using are these light cone coordinates x plus minus. So these are just given by 1 over square root of 2 time plus and minus z. Okay. And then likewise for the momentum, okay, so we have something like 1 over root 2 p0, which is the energy, plus or minus the momentum in the z direction, okay, and we're always going to take our hard parton traveling in the z direction, so this is z, okay. You should note that in these coordinates, the metric is sort of off diagonal, right? So if I look at a product like p dot x, then this would be something like p plus x minus plus p minus x plus minus p perp dot x perp. Okay, so by these I denote the transverse coordinates. Okay, and so if we take our particle moving in the positive z direction, well, then actually what happens is that one of the two, namely the plus component, becomes very large. Okay, so we typically have p plus much larger than the temperature, and the p minus becomes relatively small. Good. So now we want to embed this in the medium, and we want to see how this interacts with the constituents of the plasma, okay? And so in order to do this, okay, we're gonna have to make or we'll have to make some assumptions, okay? We cannot possibly solve this in full QCD, okay? And so I'll try to be systematic in the sense that whenever I do some approximations or assumptions or something like this, I'll try to spell them out, okay? But so really the two main assumptions that one is doing in sort of treating these interactions is, on the one hand, okay, we have a jet which can have a lot of energy, okay, but we have this huge plasma surrounding, which is a big thermodynamic system, okay, and so for that reason, the first assumption one usually does is that one considers the jet as a perturbation of the medium, okay? And so in this case, so you neglect the back reaction of the jet on the Quark-Gluon plasma, okay? And the second assumption that one makes is that since we are considering a particle which has a very, very high energy, so very large plus component of its momentum. Now, in principle, the medium can sort of transfer some of this longitudinal momentum onto the particle also, okay? But typically this will be small, okay? And so what we're gonna do is we're gonna neglect this altogether, okay? So what we do is we will neglect this longitudinal momentum transfer. Okay, delta P plus. Okay, so any kind of change of the of this light cone momentum of our hard parton when we interact with the plasma. Okay, and this is something that if you were to do this not in the Quark-Gluon plasma, but if you were to do this in cold matter, this would correspond to taking the small x limit essentially. So the strict small x limit where you don't transfer any longitudinal momentum to the other probe that you do. Good. So now,
the first assumption means that we are ignoring like any kind of a weight of the state.
Yeah. So I mean the way you so actually the way you do this usually is you calculate what happens to the jet, okay, by using this assumption, okay. Then you later realize that okay, good. There are some cases for which I have to include these type of effects. Yeah. So you put them back in, okay, but you don't make them sort of back react to the way that you treated the jet in the first place. Okay, so
yeah. So the idea is that to solve the dynamics of the jet, you
yeah.
ignore that.
Yeah. Yeah, but then I can later put it back in, essentially. Yeah. Yeah. I mean, of course, if my jet received some kick, then I know that kick has to be somewhere distributed into the medium. Yeah. And there are ways of accounting for that. And if I study thermalization, I will have to do this, right? Because I mean, then my energy needs to go somewhere, right? I want to know, you know, sort of what part of the energy never gets lost, right? It's conserved quantity, right? But it has to go somewhere, and I want to study then its redistribution. Yeah. But for the purpose of treating the hard parton, I don't need to consider it in the first place. Yeah.
Energy is distributed inside the medium.
Well, I mean, so for the moment, I'm actually not even going to lose any energy. For the moment, so what will happen is that basically this guy will receive some kicks and Gola rotations, okay? Then this will trigger radiation of the guy, okay? And then in the last step, I'll put back in sort of, you know, what happens on the medium side actually, and sort of where does this go, yeah? Okay, but for now, I'm just trying to develop the formalism and see what actually happens with this guy. Okay, I'm doing very simple things here, yeah. But let's start basic and then get to more complicated stuff, okay? Good. Okay, so now how does this help us, okay? So how should we now view this, okay? So basically if we neglect the back reaction of the jet on what is happening in the surrounding plasma, okay? The way that we can set up the problem is we can basically study this hard parton or whatever comes out of the hard parton, if it radiates or something like this, as a quantum system, which is sort of, in principle, is like an open quantum system, which is embedded into this medium, okay? And so the way it will, or the way that it's usually described in terms of interacting with the medium is through using this background field formalism, so to using a background color field of the medium, okay? So what we'll do is we'll describe our jet, whatever this means, okay, as some kind of, as a quantum system, okay, interacting with the background gauge field that I'm going to denote as A mu of x, okay, of our medium, okay, and with this starting point, okay, we can then basically now start to calculate, okay, what is happening to this hard part. Okay, good. So the way, okay, so the way this problem is then set up is basically that, okay, so whenever you consider something that is happening to the jet system itself, okay, you can use the usual Feynman rules of QCD, okay, to calculate the diagrams, okay? But now what you have to keep in mind, essentially, is that in every step of this calculation, you can always add interactions with the medium, okay? And every interaction with the medium, we will count as not increasing the order of the sort of the perturbative expansion, yeah? So I said to describe the jet as a quantum system interacting with the background gauge field of the medium, okay? Yeah, okay, good. So, so let's consider what happens in the simplest case, okay? So let's write down the sort of the lowest order diagram that we can write down, okay? So let's say we start with a quark, okay, which has some momentum p, okay, some helicity h and some color I, okay? We shoot it into the medium, okay? And so what it can pick up is it can now pick up an interaction with a background gauge field, okay? So these are going to be the ones that, you know, we will have to resum because, you know, we're sort of moving through these gauge fields all the time, okay? And for the moment, I will just denote this as kind of this line with a blob, okay? And then due to this, well, in principle, we can encounter a change in the momentum, a change in the helicity, and a change in the color state of the particle, okay? So this would just be now the particle moving in the background field, right? So this is basically this and sort of multiple insertions of this, and the physics behind this is what I'll be doing today, okay? And then in the next lecture, we'll start about seeing what happens when we consider emission of radiation, okay? So well, for today, it's not going to be anything then elastic. Okay, so here P is the momentum. Okay, H is the helicity. So basically the spin. Okay, along the z direction, and then I use as the sort of the fundamental color index. Good. So how do we analyze this interaction? Okay, so what we compute, or what we will compute, is this element of the S matrix, okay? So where we want to know, okay, what is the overlap, or what is the transition amplitude from a state where we shoot in this quark with momentum phi, okay? And so this is an in state and this is an out state, okay? And of course, well, okay, I mean, of course, so let's first write down what happens if we have nothing, okay? So if we have nothing, then of course everything stays the same, okay? So in the case of no interaction, okay, basically everything stays the same, okay? And so in the way, so the reason is that this is useful to write down is to see what, all right, there's no interaction, okay? The reason that this is useful to write this down, okay, is that, well, first of all, that's the leading term in a sum. If I start to sum all the all the interactions, right? And secondly, this will give us, will allow us to easily deduce what now changes if we interact with the background field, okay? So I'm going to denote this as 0 because we have no interaction with the background field, okay? And then this is just, just the overlap of these two states, okay? So all the quantum numbers stay the same, and then there's just some normalization, okay? So we get the same helicity, okay? Then we get a delta function in the light cone component P plus, okay? And there's a normalization factor here, which is 2P plus, okay? And then, of course, also the transverse momentum stays the same. So P perp is the same as P perp prime with the two-dimensional delta function, okay? And then also the color of the parton remains, of course, the same, right? If nothing happens. Good. Okay, so that's basically just normalization of the states. Okay, so now let's consider the case where we have this one interaction, okay? And basically, okay, we just have to evaluate this Feynman diagram, okay? So let me remind you of sort of the rules to do this, okay? So what do we have to do? Okay, so for the incoming quark, okay, we have some spinor UH of P. For the outgoing quark, we have some spinor U bar H bar of P. Okay, and the color I'm going to keep track of when I put the generator. Okay, and now what you also need to specify here is, and this is somehow always the little bit of the funny part when you have this interaction with the background field, is we want to have this interaction taking place at some well-defined space-time point x, okay? So when we study this interaction, essentially we have to switch from a picture where we are in momentum space, okay, to a picture where at this point we're in position space, and then we go back to momentum space to measure this, okay? And that is because, our gauge field we know essentially as a function of space and time, we pretend, okay? So for the interaction vertex, in this case, what we have to write is we have to, of course, integrate over all possible positions of this, that this interaction can take place, okay? And then we have the usual vertex factor, okay? So this would be IG A mu A of X, and then it's the fundamental generator TA, okay? So this is our gauge field, this is the generator, okay? Because we have a Dirac fermion, it's gamma mu, okay? But then there's also this part where we go back and forth to momentum space, okay? So we need to include, so we basically, if you want to, we need to sort of localize our wave packages to this point of the interaction. So we need to do this for the incoming and outgoing states of the fermion. So we end up with this Fourier factor e to the I p minus p prime x. Okay, good. So then with that, we have all the tools together to now compute this interaction, okay? So let's do that, okay? So let's see what happens in a single scattering here, okay? So if we now look at a single scattering, the S matrix element of a single scattering, okay? So then, well, we get an integration over d4x for the vertex, okay? Then we have to put our outgoing spinor. So we have U bar H prime of P, okay? Then we have the interaction vertex. Okay, so I'm supposed to do it the other way around, right? That's always the annoying thing, right? But okay. So we have our gauge fields, TA, okay, now because we're looking at a transition with from one color state to the other one, from this fundamental generator, we actually pick out the element I prime I, okay? Then we have our Dirac matrix gamma mu, okay? And here we have our incoming quark UH of P, and then at the end of the day, we have our Fourier transform IP of x. Okay, so what we already immediately see now, okay, is that looking now at this Fourier phase that appears, okay, and the way it appears with the gauge fields and the momenta, okay, we see that, okay, of course, the momentum transfer that we get, okay, so the change in momentum between incoming and outgoing state is actually Fourier conjugate to the space-time dependence of the background gauge field that we encounter. Okay. But no, I've contracted this with here, right? I mean, I put the color already on the generator here. Yeah. Good. So now, okay. So now the point was that the momentum transfer is Fourier conjugate to the space dependence of the gauge field. Okay. And now what we have to do next is we have to sort of implement our second assumption, which is that we neglect the longitudinal momentum transfer, okay? So inside this term, okay, there's gonna be one term which, so neglect longitudinal momentum transfer, okay? In order to do this is, so if we look at this, how the longitudinal momentum transfer appears, then we have P plus minus P prime plus, okay, multiplying X minus, okay? And so the way to implement this and get rid of this longitudinal momentum transfer is that we have to assume that our background gauge fields here carry no X minus dependence on the relevant scales. Okay, and so this is actually, I mean, if you're fast-moving parton in the medium, this is actually also relatively natural. Okay, because what will happen is that, okay, imagine you boost to the frame of this fast-moving parton. Okay, then what you will see is, I mean, you'll see two effects. You will see Lorentz contraction and time dilation. Okay, what actually happens is Lorentz contractions happens in the plus direction. So in the plus direction, your medium looks sort of very short, okay? But in the minus direction, it's sort of time dilated, okay? And that's where you see these stretched out fluctuations, okay? And that's why in the high energy limit, you then neglect the X minus dependence of the gauge field,
Yeah.
okay?
Can I ask?
Yeah.
So if you consider initial pattern as no transverse component,
yeah,
automatically that assumption is, you don't need that assumption.
If I consider what?
If you consider the initial pattern has no transverse motion.
Why do I not need this assumption?
Because this is the longitudinal direction only you have. So then you don't need that second assumption from the first place, that there is no longitudinal. Oh, wait a minute.
Well, first of all, this should be P prime.
Okay.
No, I don't think so. I think you need
Go
this assumption of neglecting the longitudinal momentum transfer. I'm pretty sure, actually.
Yeah, that's fine.
Yeah.
Go ahead.
Yeah. Okay. Yeah, because I mean, otherwise you're going to get longitudinal. I mean, as soon as you have X minus depends of your gauge field, you're going to get longitudinal momentum transfer, right? I mean, there's just no way around it, basically. Yeah. So at this stage, so okay, so to neglect the longitudinal momentum transfer, okay, we have to make our background gauge field, okay, independent of X minus, okay.
So is this calculation made better if you choose some gauge for the background field, like say light cone gauge, which is suited to the...
Yeah, I'm choosing light cone gauge. Yeah.
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 So that's what you do.
Yeah. I should have said this. Yeah. Yeah. Okay, good. So we make our, yeah, so okay, so we make our gauge field independent of this time dilated X minus direction, okay? And then basically once we do this, okay, we can integrate over X minus. This will generate us a delta function here, okay, leading to exactly this conservation of the longitudinal momentum, okay? And so then we're just left with doing here some Dirac algebra essentially, okay? And so this is fairly straightforward, okay, at least in the high energy limit, okay. So let's look at this. So if we look at the algebra that goes into the calculation of this spinner, okay, then it's a relatively easy way of doing this, okay. Okay, so what I can do is, because we're looking at a high energy particle, okay, which gets sort of a small momentum kick from the medium, we actually know that P prime and P are going to be almost the same, okay, and so if I set P approximately equal to P prime, okay, then this is just the diagonal matrix element of this spinner, okay, and this gives me then the same, so no change in the helicity, okay, and just 2 times the momentum of the spinner, okay. So with this, we can then evaluate so the P mu is contracted with a mu, okay, so we can look at what is P mu a mu now, okay, and so that is now the case where I'm actually starting to choose a gauge, okay? So typically we're going to use light cone gauge, which is in plus equal to 0, okay? Because otherwise some of these, if you choose the wrong light cone gauge, some of these statements I write don't make sense, okay? So in this case, okay, we can look at what is the momentum P mu. Well, the P mu has a large momentum in the plus direction. I can actually take the transverse momentum of the incoming particle to be 0, okay? And then what I end up with is, in particular, if I adopt this gauge, this is actually exact, okay? I just end up with P plus lower A plus, but P plus lower A plus is the same as P plus A minus. Okay, good. So now we can put all these things together. Okay, so let's evaluate this. Oh, this is actually very convenient, okay? I can just continue here. Okay, so what do we get? So the first thing we get from the Dirac matrix element, the spin structure actually didn't change. Okay, so there's no flip in the spin. That's something that's suppressed by energies. Okay, then because we have no x minus dependence of the gauge field, okay, we can integrate out part of this to get the longitudinal momentum, so the plus component conserved. So we have 2 pi delta of P plus prime minus P plus, okay? Then we have this 2P mu, which comes to the A mu, so we have a 2P plus, okay? Good, and so if you look at this part here, then that's actually the same as what appears up front here for the case where we had no interaction, okay? And so that's why I wrote it in this way. Okay, but now comes the part that's of course interesting. Okay, so what remains is now we have to integrate over the transverse position, and if you want, so the x plus sort of plays the role of a time that our particle goes through. So we have to integrate over the transverse position d2x perp. Okay, and we keep the Fourier phase here, which is e to the minus I. P minus P perp minus P perp prime X perp. Yeah, I should probably put some vectors. Okay. And then we have the coupling to the gauge field, which is IG, and then it's just the minus component staying there. So we have IG integral dx plus, and then we have A minus A, which according to our assumptions only depends on X plus and X perp. Okay, and here we have the generator, fundamental generator, I guess I prime I, okay, which gives us the transition between the two color states. Okay, so now we can see what actually changes and what does not change. Okay, so if we now look at the outcome of this, we say certain things that stay the same. Okay, so up front here, okay, we see that somehow spin and longitudinal momentum unchanged. Okay, but what we see is that looking at the other components that are up here is we say we have an exchange of color, right? So color exchange, so that leads to a change of the color state. Well, I mean, that's of course obviously clear whenever you attach a gluon, right? And the other thing that we see is that because this gauge field has some transverse structure, and of course the transverse structure of the gauge field, if you decompose it into Fourier mode, is sort of the transverse momentum that is carried by the gluon, right? So that transverse momentum that is carried by the gluon, okay, is then transferred here. Or well, if you want to do all of these terms over here, you have exchange of transverse momentum and color exchange, okay? Good. So now, good, this is one interaction with the medium, okay? But, well, okay, I mean, the medium is in some sense dense, okay? So just looking at a single interaction with the medium doesn't get you very far, okay? And so in principle, what you should now consider is having an arbitrary number of insertions, okay? And so, yeah, I mean, you can do it in this way, okay? So that you can now say, okay, if you want to look at Sn, right, then you basically set this up with having n exchanges, okay? And then at the end of the day, you have to sum over all the possibilities of having n exchanges, okay? You can do this, and actually as an exercise, because this is actually sort of fun, okay? You can compute what happens if you do two exchanges, okay? Because there you actually, you learn perhaps a little bit more, okay? Because you can find phenomena that we didn't see here. So calculate what happens for two exchanges, okay? And if you can't figure it out, you can follow some lecture notes by Carlos Salgado. Okay. Now, the story is, if you actually do this, essentially what happens is not particularly complicated, okay? Basically, you'll never, I mean, so what you'll never have is some change of the spin and some change of the longitudinal momentum, okay? And through every interaction, you basically just generate more of these terms, okay? And so you can formally compute, I mean, if you start to compute the second term, what you'll easily start to see is that this kind of term that you get here exponentiates, okay? And so if you then just sum everything, okay, what you get is, so you look at this S matrix element and now at the real S matrix element for the propagation inside the medium, so just neglecting radiation for now, but summing over an arbitrary number of gluon exchanges with the medium, okay? What you find is that you still have this structure of spin and color staying intact, okay? So you get the delta functions in longitudinal and transverse structure, okay? But now this exchange of color and momentum with the medium exponentiates, okay? And of course, the momentum transfer then is the sum of the momentum transfer of all the exchanges, right? Which is which you get as Fourier transforming the final result, okay? So you get this as Fourier transforming e to the minus I p per prime. No, wait. I guess it doesn't matter actually because it's odd anyhow, okay? And what you end up here is the exponentiated form of this, okay? Which I'll denote in the following, okay? So what this is a light-like Wilson line, okay? So when I write this V of X perp, okay, what this is it's the path-ordered exponential, okay, of the integral IG, and you have an integral over X plus, okay, from where you enter the medium to the end, of your gauge field as a function of x plus and x perp. So you just see that this is sort of the leading order contribution, which then exponentiates. And in principle, I mean, if you're used to, say, okay, like for instance, you're working in lattice QCD or so, right? I mean, this shouldn't be surprising to you at all, okay? So, I mean, if you've got a particle moving through a medium, okay, along some path, right? The first thing you pick up is the Wilson line, okay, along the path that you go, okay? And so as long as we work in this iconal approximation, right, our path is actually just a straight line path, okay, in Z with no deviations up from this path. Okay.
Sorry, could you just read for me this reference?
What
is it? 0? You're giving
3443. 0712 3443.
3443.
Yeah.
One point here, you had this that term.
I set p perp to 0. Yeah, and well, I mean, so you can either set p perp to 0, right? If you were to add something like, well, I guess it would be minus p perp a perp or something, right? What you can see is that this is energy suppressed, right? Because p plus is large and the transverse momentum is small. Yeah. And the other one vanishes by gauge choice. Okay. Now, in principle, it's so. If you don't buy this exponentiation, there's also a somewhat simpler way of arriving at the same result, and this takes maybe 5 minutes, but I think I'll show you. Okay, because this is sort of the basic building block that goes into everything. Then, so I think it's good to have maybe even another idea of where this comes from. Okay, so you can sort of. So, I mean, what you learn from the single scattering is definitely you don't have an exchange in longitudinal momentum and you don't have an exchange in spin. Okay? Now, if you don't have an exchange in spin, okay, then basically you can also just look at what happens at a scale, to a scalar. Okay? And this is a little bit easier to calculate than working with all the Dirac structure. Okay? So, formally, you can get this by summing the series and blah, 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 right? If you don't believe me, but let me give you sort of another heuristic derivation of how to get this, okay? So if you say that, okay, there's, since there's no spin exchange, right? Since spin doesn't play a role, you can consider a scalar, okay? And for the background field, okay, we adopt the light cone gauge, okay? Where we set a plus to 0, and then actually we take our gauge field to be just this dominant minus component. So we only consider the gauge field in the minus component, which is the only one we couple to. So we only get a gauge field if we have a minus component, so we put a delta function up front, and then this is just the minus component of our gauge field, okay? And then if we look at the scalar, charged scalar, right, then what we have to solve is the Klein-Gordon equation for a charged scalar, right? So we solve d mu of our field is equal to 0, okay, where now d mu is, of course, the covariant derivative, so that's the ordinary derivative minus the insertion of the gauge field. Okay, so if we write this down, okay, what do we get? Well, we have to look at all the different contractions. So this gives d minus of d plus. Okay, so lowering the minus component gives me the plus here. Okay, then I get this the opposite way. I get d plus d minus. Okay, so only d plus because I only have a minus component of the gauge field. That's the only one where I actually have to care about being the derivative being covariant. Okay, and then I get the second term, which is di. Okay, acting on this field is equal to 0. Okay, and now we can do sort of two simplifications and then basically very quickly get to this result of the Green's function. Okay, so the first is because our gauge field doesn't carry an x minus codependence, right? We can always pull the d minus, so this minus derivative through the gauge field that appears in the covariant derivative. Okay. What?
We can get you a first capital D plus.
Yeah.
With the small d minus. Same.
So I have d minus, okay, and I have d plus, d plus. So here I lower the plus to be a minus. This gives me this one, and here I lower the minus to give a plus. So you actually get this combination. Yeah. The point is the combination doesn't matter because the gauge field is x minus independent. Yeah. Okay. So you can pull it either way. Okay. So I mean, well, let me maybe do this in this. Let me just say this, right? So I can just, without loss of generality, write it like this. Okay. Okay, because where I use that A only depends of x plus and x per. Yeah. Okay. So now the other thing that we know is that and I mean we can see this also from solving this equation, right? Is that we're not going to have any longitudinal momentum transfer to our particle, okay? And so what that means is that if we prepare our particle as an initial plane wave with a well-defined P plus component, okay, then that P plus will stay the same as throughout the whole evolution in the medium, okay? And so what we can do is now we can go to a mixed space representation, okay, where basically our, I mean, we write our psi of x as a plane wave, essentially, okay? So this is some psi p plus of x plus and x perp, okay? And then the x minus dependence just remains this plane wave, okay? With this, we can then explicitly pull this down over here, okay? And so this covariant derivative, so what this really means, this derivative then simply becomes I P plus, okay? So with this, we then get an evolution equation, which actually now looks like evolution just in this variable x plus, okay, which we should think about the time that we pass through the medium, okay? So we have this sort of modulated wave that passes through the medium in the x plus direction and receives this transverse kicks, yeah? So if we look at this object, then we get that d, so that now the covariant derivative we can insert. So we get that the time derivative, or the d plus, so the derivative with x plus of this field, x plus and x perp, okay, now essentially receives two terms. So one that comes from the other term here, namely from the gauge field insertion, and the other one that is related to the transverse dynamics, okay? So if we just move the covariant derivative over, we just have here our IgA minus inserted at the corresponding positions, okay? And then here we have, so from this we got an IP plus, so we have to divide by this and bring it over. So we have minus di over 2I d plus, okay? Acting on this now wave function of the object that we're studying as a function of x plus and x perp. Okay, and so now this is something. So now this has a very very intuitive form in principle, right? You may even, you may even make this sort of look more intuitive if you multiply the whole equation by I, okay? So if you multiply the whole equation by I, you have I dt of this wave function is something, okay? So this actually looks very much like a Schrödinger equation, okay? But now a Schrödinger equation in 2 dimensions, okay? Where this term here, okay, is like the kinetic term, right? So upon multiplying by I, right? So you have p squared over 2m. P squared is the derivative. The plus component of the momentum plays the role of mass, okay? So this is like sort of free propagation of our particle in the transverse plane, yeah? And then we have the interaction with the gauge field here, yeah? As represented by this, yeah? So this is, so we get this 2D Schrödinger-like equation, okay? For, in this case, I wrote this for a field, but of course you get this also if you study the propagator. Yeah? So for, let's call this the Green's function. Okay? I mean, if you do this for the Green's function, you just put a delta here, but you don't, I mean, doesn't net much, okay? Good. So the way this is useful is that now, of course, we can also sort of look at two different levels of approximation that we can use or we can take here, okay? The first one is, of course, we can look at this in the strict iconal limit. Okay, and this is the limit really formally p plus goes to infinity, right? Now, if p plus really goes to infinity, then this term here in the back is inversely proportional to p plus, so I can neglect this altogether. Okay, then I'm just left with solving dt phi is IgA minus phi. Well, this is easy to see that this exponentiates, and because this is a matrix which doesn't commute with itself, it ranges into this path-ordered exponential over here, okay? So in the strict iconal limit, p plus going to infinity, okay, what you find is that after some time of propagating to the medium, okay, so let's say we look at some position y plus and x perp, okay, we get our initial, well, I mean, we get basically just, I'll write it. So we'll get our initial condition, okay, at some earlier time, x plus and the same position, okay? But this is now multiplied by the Wilson line along this path, okay? So by the path ordered exponential of Ig integral, and the integral now goes from x plus to y plus, and I'm just going to write dx plus because I don't want to put any twiddles, okay, of our gauge field, x plus and x perp, okay. Now, the thing is that, okay, in principle, one can now also go one step beyond this, okay, and at least formally solve this equation, okay? And so the way you formally, I mean, the way we formally solve an equation like that, and I'm sure you've seen this in quantum mechanics, is to a path integral, okay? So you can write down a path integral, okay, whereby basically you consider all the possible paths of the object from one position to the end, okay? And then you just weight the different paths by the action, okay? So the action is going to have two components, so it's going to have essentially this kinetic term, okay? But then at the same time, you also pick up this Wilson line along this path, okay? So, so beyond the iconal limit, okay? Okay, and so what you're going to get, and well, okay, what you're going to get is that in addition, you include the dynamics of this term. So now you actually, I mean, here information is local because basically you're not moving around in the transverse plane, but now you also have this effect of sort of quantum diffusion in the transverse plane, okay? So you can write this as an integral over different paths. So path depends on your time variable x plus, okay? And of course, at the beginning of the path, you are at some position x perp, and at the end of the path, so at y plus, you're at your final position, okay? And then you integrate over all possible paths. You take your action, okay? So the action in principle is just the free action, right? So it's P plus over 2. So this is the mass, right? So this is like m over 2, okay? And then it's the sum of the velocity squared. So the velocity is dr by dx plus, okay? But then you also have the Wilson line along this particular path, okay? So I'm just gonna write this as a Wilson line V, which depends on this path r of x plus, okay? And so, I mean, so this was, I mean, this was actually the equation that Jean-Paul was essentially also discussing yesterday briefly in his colloquium, okay? And so the important point here is the physics, right? So if you stay in the strict icon limit, what this includes is, as we discussed here, this includes collar rotation and transverse momentum exchange. Okay? So the picture here is that you have sort of your particle and it stays on the straight line path, okay, but it exchanges collar and gets in net some kick, okay? What you have here in addition is you have your quantum diffusion of your wave packet, right? Because sort of for every interaction you need to localize it at some point, right? But if you localize a quantum mechanical wave packet, right, the first thing it will do is it will spread out in space, okay? And this is what is characterized by this term. I mean, the spreading out is suppressed by energy because that's what plays the role of the mass, okay? So, but here you have the spreading of the wave packet, okay? Which is actually not important, not really that important if you just consider this propagation, okay? But it's very important when you start to calculate radiation or radiative emission from this. Good. So, okay, so now we have basically calculated this this S matrix. So this is essentially just to motivate the result that we got here and extend it a little bit. Okay. So now let's see what this means for kind of the simplest application that we can do is where basically we just have some hard probe produced and then it traverses through the medium without emitting any radiation. Okay, and let's see what comes out there. So okay, so let's move on and now consider a physical process.
Acting your Wilson way. First one,
yeah, I mean, there's also there the Wilson line is not taking along a straight line path anymore, right? So it's, I mean, you're doing a path integral over over all the possible weights which have these oscillatory weights, right? Yeah, and well, but I mean the weight is oscillatory, right? So I think, I mean, so at the end of the day, okay, so what we'll see is that when you calculate the radiation, you end up with a similar Schrödinger equation, in this case, not for essentially a single particle, but for somehow a three-body system of emitter and emittees. Yeah? The way you actually solve this is usually by solving this Schrödinger equation. At least that's...
The normal path integral will be for I-10 action.
Mm-hmm.
If you go away from the classical action, then all the other fluctuations typically suppressed. Are there arguments here for the oscillation for the iconal part, and then you have some fluctuation of all? Can one think of that?
Let me just flip on the microphone again. So I mean, the cases where you compute, so I mean, the cases where you actually compute the path integral is usually where then you assume a very particular form, okay, of the interaction potential, essentially. Yeah? And in this case, so in these cases, you can compute this another, you reduce this to an harmonic oscillator where actually the classical path is at the end the only one that contributes. Yeah? So where you can compute this path integral analytically. Yeah? So that's usually the way you do it at the end of the day. Yeah? Or you solve the Schrödinger equation. Yeah? So that's why it's also good to kind of have both of these pictures in mind when it comes to understanding some of the expressions that determine the rates later. Yeah. Okay. So good. So now let's try to let's start to put this to work a little bit. And so I mean, so far we've just embedded our particle and somehow shot it through the medium, right? Now, if we want to look at something like a physical process, okay, then what would actually happen is that, okay, we have some hard matrix element or so for producing this particle, okay, and then afterwards it would sort of traverse to the medium, okay, and at the end we would measure something produced, okay, and measure its momentum, okay, and so what at the end of the day we want to measure is some cross section or so, okay, and so if we want to compute the cross section, then of course we have to square this whole process. Okay, so you have to compute m times m star. Okay, so if we assume we can somehow factorize this propagation in the medium from the hard production process, and the reason that we would typically assume this is because the hard process is quick and then interaction with the medium happens afterwards. Okay, then basically what we have to do is we have to now take the hard matrix element, multiply it with the S matrix, that's sort of our amplitude, okay, and then multiply this with its complex conjugate to get the cross section, okay. So structurally, if we look at the differential cross section now for this process happening in the medium, okay, so this would be something like this, okay. So cross-section as a function of energy and transverse momentum, okay? Then we get this by, well, we produce this hard matrix element. So we put the amplitude here where we produce the parton with some momentum P, okay? And then we put the complex conjugate amplitude here where we measure the same momentum K, okay? But in principle, we can here start from a different P prime, okay? And again, have our hard matrix element. So this is like Logan did it, right? So this is the amplitude, this is the complex conjugate amplitude. So I'm drawing this as going backwards in time here. Okay, sometimes I will also sort of flip it down here, and then it'll be like this closed time path. Okay, but for now I'll do it like this. Okay, so if we compute this, we have to integrate over the intermediate states, so P and P prime. Okay, then we have to sort of, in the S matrix, we have to sum over initial and we have to average over initial and sum over final states. Okay, so in this case, this would be the collar. Okay, so we get for the averaging a factor of 1 over number of collars if this is a fundamental parton, and then we sum over incoming and outgoing collars. Okay, then in this amplitude we have our S matrix, and I'm neglecting here spin here because it doesn't play a role. Okay, we have an S matrix for P going to K. And here we have the complex conjugate of the mass matrix for P, and I'm going to call this actually not P, but this is some different momentum. I'm going to call this P bar. Okay, so bar to denote that it's in the complex conjugate amplitude of K. Okay, and then I have my hard matrix element of P and hard matrix element of P bar. Okay, so now, in this integration, so I mean, when I write integral P, this is something like integral d2P perp over 2 pi squared, okay? Integral dP plus over 2 pi 2p plus. Okay, so doing the p plus integrations is of course easy, right? Because I mean, the longitudinal momentum is conserved here in both the amplitude and the conjugate amplitude. And so at the end of the day, this just sets all of these longitudinal momenta equal to the one that we measure in the end, which is k plus. Okay, now, so the interesting part is somehow in the transverse dynamics. Okay, so for the transverse dynamics, what do we get? So if we now insert the structure of our S matrix, then, well, we have these two transverse momentum integrals. Okay, then we have, I think we still have the expression over here, right? So we have now the Fourier factors over here. Okay, so we have e to the minus I k p per k minus p perp x perp and e to the plus I k minus p bar perp x perp bar. Okay, so because I have independent integrations in the amplitude and the conjugate amplitude, so I should put them here as well. Okay, so integrating over the transverse position of the scattering in the amplitude and the conjugate amplitude. Okay, and then I have, and I should have said this, right? I mean, of course, when we're doing this and we're measuring, right, what we're actually doing is we're taking somehow medium averages of this background field. Okay, and I don't know if I'll get to this today, probably not. Okay, so I'll explain in the next lecture how to take these medium averages. Okay, so we get the medium average of now this object over here. So if I complex conjugate this, I can write this as reversing the indices and doing the Hermitian conjugate. Okay, and then this is when I sum over I and I prime. This is like a matrix product that's traced. Okay, so what I end up getting over here is something like 1 over NC. I'm going to write it as a sum for now. Okay, so it's VI. What did I have? It doesn't matter, right? I prime I of the position X perp. And here I have I prime V dagger of X perp bar. Okay, and this on average. Okay, and then we still have the hard matrix elements at P and the conjugate at P bar. Okay, so now this looks fairly complicated, but the mess will clear up in a second. Okay, so now we can simplify this in several ways, right? So if we consider a homogeneous medium, okay, then in a homogeneous medium, we have translation invariance, okay? And so actually the expectation value of a 2-point function does not depend on the center of that 2-point function, but only on the relative separation, right? You can shift it around arbitrarily, okay? And so for a homogeneous medium, this only depends on the difference here, okay? So what that means is that, okay, now when you're integrating over x plus and x plus bar, okay, you can change this to an integration over the center of the two coordinates, okay, and the separation x perp minus x perp bar, okay, and so if you work out, these Fourier factors, okay, then what you will see is that, so the k appears with sort of the difference in the phase, okay, p and p bar appear in two places, okay. And so you can write this as a sum of the two p's and a difference of the two p's. What will happen is that once you integrate over the center of mass, the difference between the two p's, okay, will become a delta function, okay, therefore setting the transverse momentum equal in the amplitude and the convex conjugate. Yeah. So for homogeneous system, transversely homogeneous system, okay, this average then only depends on the difference, and that sets the transverse momenta equal in the amplitude and the conjugate amplitude, okay? And so what you end up getting at the end of the day is that you're just left with one integral over the transverse momentum. Let's, for instance, call it P, okay? And as soon as you have P equals Z to P bar, then this Fourier factor is just IE to the IK P perp, and then you have X perp minus X perp bar, okay? So you still, wait, I should probably write the spatial integration here, yeah, sorry. Integral d X perp minus X bar perp, okay?
Sorry,
So,
can I just, I'm just trying to understand this notation. What is K?
what is what?
What is K? What is the momentum K here?
What K? There's no K. So the momentum K is the momentum that I measure at the end.
Okay. So
Yeah, so K is the one that I measure at the end, right? So K is the one that's being measured here.
So that's a transverse momentum.
So K perp is the transverse moment. Ah,
Okay.
yeah, this is transverse. Yeah, of course, sorry.
So this.
Yeah, I just forgot to put the perp here.
Okay,
Yeah.
so this is the transverse momentum,
Yeah.
and these M's are the initial distributions.
So these are the hard scattering matrix elements here.
Okay. Okay.
Yeah.
Mhm.
Yeah. Okay. And so, so what we get here is now this, what is called the so-called dipole amplitude, right? So after I sum the indices, this is a matrix product in a trace. Okay. So this is the trace of two fundamental light-like Wilson lines, V and V dagger, okay, at the two positions, okay? And here I have just the hard matrix element squared, okay, evaluated at P plus equals K plus, okay? And so what we now see is that, well, okay, I mean, actually, so once I square this, okay, basically, I mean, I'm basically assuming that this is just the cross section, okay, so let me just do this by wiping here, okay, so this is just the differential cross section, so because K plus is P plus, but then now differential with respect to P perp, yeah. Okay, so now let's look at, so what is now the physics that comes out, okay? So for now, ignoring radiation, okay, we can measure a cross-section with respect to transverse momentum, differential cross-section, okay? And what we see is that the effect of the medium is we get sort of the same cross-section like we have in vacuum, right? So in vacuum, we wouldn't have this kind of propagation, okay? But now what we see is that, okay, this is essentially convoluted in momentum space with the Fourier transform of this operator. Okay, so what we see is that if we look at this factor here, okay, then what this describes is somehow a transverse momentum broadening. Okay, so adding transverse momentum to our produced particles as they pass through the medium, okay, and that is exactly what is encoded in this object over here, okay, which, so this is called the dipole amplitude, okay. Okay, why is this called the dipole amplitude? Well, it's very simple, okay. So if you look at the amplitude of this process, right, then we had a quark propagating forward in time, okay? And then in the complex conjugate amplitude, we have a quark propagating backward in time, okay? But this basically looks like, in terms of color, something that's propagating like an antiquark propagating here, right? So if you do this sort of Shinha-Keldysh construction, right, then it looks like something where you have a collar dipole, so you have two colored particles that in total are in a singlet that propagate together in amplitude times complex conjugate amplitude. And this is exactly your collar dipole. Okay, so I think I have 5 more minutes. I think there's no point in starting something new here. Didn't really get as far as I wanted to, but that's okay. Are there questions more?
Here you have not considered any radiation, just the propagation of photon and interacting with the medium.
Yeah.
And that itself gives the broadening.
So that just gives you momentum broadening. Yeah, exactly. Yeah, yeah.
But you can also include radiation, the broadening will be different and that.
Yeah, so, so this quickly becomes very complicated, okay? So you can I mean, you can include, so you can calculate medium-induced radiation, okay? You can, yes, okay, and then in principle that effect, I mean, that medium-induced radiation, I mean, depending on what you study, right? It always depends on what you want to study, right? But if you study, say, the leading parton also, right, then that medium-induced radiation will also take away transverse momentum, right? In this case, you need to then calculate this differentially, how much transverse momentum is carried away, and this very quickly gets very complicated, but yes, yeah. You can do this, yeah. And this happens, right? I mean.
And here you have not considered any, either a thermal medium or anything. It's just medium rest.
Yeah, so this is yeah, that's actually a good point. So this is true, right? So I mean, all I've set up, I mean, the assumptions I've made, I spelled out essentially, right? I said that okay, it's a high energy particle. We treat this as a background medium with a classical color field, and this is what we can calculate. And in fact, I mean, this kind of definition that I wrote down here, right? This is something that, for instance, also has been calculated in the Plasma, right? So the very early stages, right? There you literally just take this operator definition, right? You have a sort of a lattice discretization of your classical fields, and you compute this, which you evolve in real time in that case, and then you're able to compute this correlator of light-like Wilson lines. One should say that if you do this non-perturbatively, and I'll say this tomorrow actually, this is the way I've written this is not gauge invariant, because what you still need is you need to add connecting gauge links between the ends of your Wilson lines in the transverse plane. Yeah.
A quick question, because this this object in the bracket, which we call the dipole, this dipole object, which is within this bracket, so it has a very delicate evolution in high energy. Say it governed by, say, BFKL or BK equation. So does that mean that that kind of evolution also exists for this momentum broadening, the whole object?
So, okay, so this is, so that's a very delicate question. So, I mean, so how do you get evolution, right? I mean, what you do is you compute radiative corrections essentially, right? To, in this case, momentum broadening, right? So the point is, if you do this in the, I mean, if you do this in high energy in CGC also, right, then essentially what you have is you have this shock wave medium, right? So you have a very thin medium, okay? And I mean, the radiation process is just simpler. Yeah, so the radiation happens, I mean, you never radiate inside the medium, so to say, right? You radiate either before you scatter or after you scatter. Now, inside the medium, okay, what you actually have to consider when you emit radiation, right? So now imagine sort of your interaction with your, I mean, with your nucleus is stretched, right? Then what you need to consider is that actually you have interactions throughout the entire emission process, okay? So now let me think a little bit more, okay? So now you're asking if you have some kind of small x evolution for this. In principle, in small x evolution, you're resumming soft logarithms, which you still have inside the medium, okay? You don't have collinear logarithms inside the medium. So something like D-glub you wouldn't have, right? But in principle, there should be something like this, but I don't think it has been worked out. Right? Maybe Jean-Paul can comment, right? It's, yeah, it's, yeah, so it's like, yeah. I mean, yeah, so this is, I mean, so there are works which have looked at this, right? But it's not, I mean, it's not, I mean, it's also for Q hat, right? I mean, you don't have it for the full dipole amplitude, so to say, right? I mean, you don't have an evolution equation for the full dipole amplitude, right? In that sense, right?
The momentum that boils down to evolution.
Yeah, I don't like that actually, but yeah. Yeah, okay, yeah. So, so I think the answer is yes, this physics should be there, and this has been looked at, okay? But I think it's not something that's commonly used also in when you actually do phenomenology also, right? I mean, I've seen nobody using this computing radiation. Yeah.